Welcome to the third class of this course, and I'll just briefly revise it during the last two classes what we have introduced. So we went through some basic microstructure and the formation of crystals, then grain structure, then we talked about we talked about the history for the field ion, the development through the field ion microscopy. Then related to some basics, we have correlated the shape of the structure of the tip or the samples, and how Professor Mueller has developed this field ion microscope. Fine. So basically Professor Mueller in 1951, as you see in the slide, what he has done is he has sharpened a very needle shaped specimen, okay, and this needle shaped specimen was cooled down to liquid, it's a sub-zero temperature, mostly on liquid nitrogen temperature, by putting liquid nitrogen. Then he has inserted an imaging gas which might be helium, neon or argon can be used. Usually the first time he has used the hydrogen. Then this is the gas inlet. Then and he has applied a very high positive potential, fine, as a very positive potential such that the imaging gas ions gets ionized, fine. When it gets ionized and due to the very high voltage, the positive voltage on the tip, there will be a large amount of electric field or the electric field lines, correct, electric field strength, and these gas ions will accelerate along these field lines, and there is a channel plate, or we can get the fluorescent screen where these gas ions gets hit to the positions on the fluorescent screen, and the hitting of these positions or the is directly gets this typical FIM image, which is a field ion image, where you can see these bright spots. These are the spots or the locations where these imaging gas ions are get hit on those regions. So that's why you are seeing the bright contrast, correct, and these bright dots each corresponds to the actually the image of the atom probe tip. So you have a tip and these are the surface atoms, and if you magnify these surface atoms, they have a certain crystal structure. These atoms are in the form of some crystal structure or the orientation. And as we also explained that these imaging gas ions which are get ionized on the tip, those forms this FIM image, okay. And we also described the formation of these circular things, and you can see that these are the circular things and they have a certain orientations, correct. And if you see if you see an atom probe tip, then if you zoom out this region, then you can see that these atoms have a certain terraces, correct. These are called terraces, atomic terraces, and these are related to the crystallography, fine. So I have given you example of a schematic where it shows the 100 direction, correct, and you will have a cubic symmetry. So those terraces actually corresponds to the crystallographic nature of the atom probe tip, and due to these terraces, okay, the local curvature effect, this is the local curvature effect, the electron gets here, it's a deficiency. Your electric field concentration is much higher at these locations than the flat surfaces, correct, due to which the ionization of the gas atoms takes a much higher rate at these locations, and that's why you see these circular bright spots, the bright spots which are oriented circularly, and each circle corresponds to a certain crystallographic direction. These are related to a crystallographic direction, fine. So this is the this we have covered in the last class, and in the next what we will go through is yes, we have seen that how these gas atoms are get ionized, and how these can be used to image the surface of the tip. Okay, so now in this class what we go through is some basics related to how these gas atoms gets ionized. Okay, gets ionized. So we'll go something related to some basic physics, which is related to the ionization of these gas atoms in presence of a metal surface, in presence of a metal surface. Fine. So, and in the first class we already described about the potential energy curve of between the two atoms, correct. So based on that, this is the similar thing here. This is the potential energy curve, this is the potential energy curve with the distance. Okay, and this plot is without any electric field. Okay, and the field induced removal of an, so this shows that so if you have a metal surface, so this is your metal surface. Okay, so you have a metal surface, and if you have a gas atoms in the vicinity of this surface, how the potential energy will change as these gas atoms approaches the surface of the metal. Fine. So this is the potential energy curve for that particular case, and it is very similar to the what we talked about the Leonardo-Jones potential curve, where we have given the two atoms, the potential energy curve between the two atoms. This is a similar curve. Okay, so based on that, this diagram is a potential energy as a function of distance to the surface of an electron which is present inside the gas atom in the vicinity of a tip, or in the absence of the electric field. Tip means it's a metal, it's a metal surface. Fine. This is a metal surface, this is a vacuum, and as your gas atom which is having an electrons are far apart. Okay, so at long distances you can see that the potential energy is almost 0. Your V is equals to 0. It means that electron experience minimal interaction with both metal and the gas atom. Okay, so the potential energy is essentially 0. As this gas atom with the electron moves near to the metal surface, this is the metal surface, this is the metal surface, and as it moves near to the metal surfaces, it experiences the first thing is attractive forces. Attractive forces. What is how these attractive forces comes up? It is attractive forces at intermediate distances, correct. So you can see that your potential energy curve starts getting negative, it reduces up to a level where the potential energy is minimum. Okay, so this is related to your attractive forces. Okay, so it means that as the electron from the gas atom or is approaches the surface of or the metal surface, an attractive force due to the charge effect will comes into play. Okay, and this is charge effect is induced by the metal, is the metal on the electron, correct, and it experiences an attractive forces. It is very similar to the van der Waals forces as we described during the one atom to another atom interaction. Okay, so and this leads to the decrease in the potential energy to a minimum value. Okay, and it leads to a minimum value. But as you go further near to the metal surface, you can see that the repulsive forces builds up. So this is called repulsive forces. Repulsive forces builds up. This is due to this leads to the increase in the potential energy. Increase in the potential energy as the gas atom moves near to the metal surface. So there is a second type of forces which is called repulsive forces builds up. Okay, and these repulsive forces are at very close distances. Fine, at a very close distances, and this is due to the overlap of electron cloud of gas atom and metal. Fine. This is due to the overlap of the electron cloud, negative and negative charge, due to which there will be a repulsive forces which increases the potential energy further. Okay, and as it goes near to the surface, these repulsive forces increases significantly. This is directly what we call it as a Pauli's exclusion principle. This is related to your Pauli's exclusion principle. Fine. This is the basic thing which is the potential energy change as the gas atom approaches the metal surfaces. Okay. So now there are third point is the potential energy at the minimum potential energy position. Fine. And this minimum potential energy person represents the equilibrium distance. It represents the equilibrium distance between the electron of gas atom and the metal surface. Okay, so this is the equilibrium distance between the gas atom, electron of the gas atom and the metal surface. So at this point, both the repulsive and the attractive forces are balanced. Okay, so this is clear now. So this is at this position, both the repulsive and the attractive forces are balanced. Okay, so now the slope of the potential energy curve. The slope of the curve means this particular. The slope of the potential energy curve represents the force acting on the electron of the gas atom. Okay, so in this the slope changes, it shows the attractive force. Here the slope is changed, here the repulsive forces, but at this minimum point your slope is 0. Your slope is equals to 0. So it indicates that the net force on the electron at this position, at the lowest position, is 0. At this position it is 0. Okay, and this potential energy curve of an electron of the gas atom in presence of the metal surface is the basis for field ionization. Is the basis for field ionization. Is the basis for the field ionization, and it helps to understand the phenomena like electron scattering, adsorption, and also the chemical reactions. Chemical reactions on the metal surfaces. Okay, I hope you have understand now this potential energy curve of a gas atom with an electron near to the metal surface without presence of electric field. Okay, this is very important. This is without presence of electric field. Now, in the next thing, if we apply an electric field, okay, you have a same metal, you have a gas atom with the electron cloud. Fine. When you apply an electric field, the whole potential energy curve gets distorted. It gets distorted. How it distorted? The potential energy curve, it gets distorted in this way. Fine. And now you can see that as you approach to the metal surface, the gas atom metal surface approaches. Okay, so you can see that there is a attractive forces. It goes to a minimum value, which is a minimum potential value. Okay, this particular energy, potential energy, then again it increases as a repulsive forces. Correct. This particular hump is called the tunnel barrier. So your electric field, whatever you have applied, it should be enough such that the minimum potential energy of that particular gas atom should be above the Fermi level of the work function of the metal surface or the metal surface. Okay, so the position of this minimum potential energy should be equal or higher than the EF or the Fermi energy of that particular metal atom. When it is equal or higher than the potential energy atom, then what will happen is tunneling process can takes place. Tunneling process can takes place. Okay, if this potential energy of that particular electron in the gas atom, if the electric field is enough such that that potential energy is at the level of Fermi energy of that metal, then the electron tunneling can takes place. It can go through this tunnel barrier. So this is called tunneling process which is taking place, and due to which the field ionization, the ionization of the gas atom takes place. Fine, the electrons will travel through tunneling process towards the metal atom if the potential energy, the minimum potential energy is equal to or above the EF or the work or the Fermi energy of the electron. Fine, assume that this minimum potential energy is at this level by application of the electric field. There is no way that electron can tunnel through this barrier. Okay, so the minimum requirement for the electron to tunnel towards the metal surface is the minimum potential energy should be at the level of the Fermi energy of the electron metal surface. Fine, now the distance. So the distance, the critical distance which is required for the tunneling process to takes place is called the x critical. It is the minimum distance for which is necessary for the tunneling process to takes place. Correct? And if the electron or if the gas atom with the electron goes below the xc, means it comes near to the xc, you can see that the repulsive forces comes into picture, and due to this repulsion action your tunneling process cannot takes place. So the electron, the gas atom with the electron should be either at xc or greater than xc. Then only this tunneling process can takes place, and this is the second condition. First condition, the electric field should be enough such that the minimal potential energy is at the equal of the Fermi energy of the metal atom. Second condition is the gas atom distance should be equal to xc or it should be more than xc. As if it is less than xc, your repulsive forces comes into picture, then tunneling process cannot takes place or the electron cannot go through the metal by the tunneling process. Fine. So these two concepts are understood now. So how to measure the xc? So xc can be given by I0. The I0 is the energy of the first ionization of the gas atom, which is given by this one I0. Phi E, which is the work function of the surface of the metal, and F is the electric field which is applied. Fine. So your xc, the minimum distance which is required for the tunneling process to takes place can be given by this particular equation. Okay. Okay, so I hope now and this total theory was developed by Professor Gomer, which is at Harvard University, Cambridge in 1961. Fine. So this is the basics related to the field emission or the field ionization of the gas atoms in the vicinity of the metal atom. Okay. So if we revise it, so you can see that the energy of the electron from the gas atom must coincide with or higher than the lowest available conduction level in the metal, which is called close to the Fermi level, which is called EF, as I explained in the before slide. Okay, and if this condition is not fulfilled, there is no vacant energy levels in the metal available for the tunneling of the electron. Fine. So the minimum potential energy should be either near to the EF or more than the EF. So your electric field should be should be such high, such that this barrier can the electron can tunnel through the barrier. Fine. So as a result, this process can only takes place when the gas atom is beyond a critical distance, which is called xc from the surface. Okay. So ionization is impossible if x is less than xc, because here the repulsive forces takes into action. But if the ionization is maximum at x equal to xc, where your potential energy is minimum, and the main condition is it is to be near to the Fermi energy level. Fine. So this is the basic related to the electric field induced ionization of the gas, and it is nothing but the removal of electron from the gas atom towards the metal, so that the imaging gas gets the positive charge. Okay. So if you have an atom probe tip, you are applying a very high potential bias, positive potential bias. You have a metal surface. This metal surface has a certain structure. The atoms are arranged in a crystallographic structure. You are inducing, you are putting the imaging gas, which might be neon, argon. Fine. And these gas atoms, due to this very high positive potential, it will go near to the surface, and at a distance of xc, so if you have a tip, you have this particular gas atom at a distance of xc, the electron from the gas atom in presence of electric field, meaning in sufficient electric field, the electron can travel towards the metal surface. As these electrons travels to the metal surface, these atoms gets ionized, developing a positive potential, positive. Fine. And if you put up a screen or the phosphor screen, then what will happen, due to this positive potential at the tip, these electric field lines will accelerate these gas atoms, which goes towards and hits to the fluorescent screen. Fine. So these gas atoms actually are the image formers of the tip surface. These actually, they wherever the position which they are hitting on the fluorescent screen, it is exactly the position of the atoms or the crystallographic terraces. Correct. More importantly, crystallographic terraces the develops on the fluorescent screen by these imaging gas atoms. Okay. So I hope the physics behind this field ionization is clear now. Fine. So here this is just an schematic taken from this particular book, Atom Probe Microscopy, where this is the atom probe tip. This is atom probe tip, and as you can see that these circular things are nothing but the crystallographic terraces of that particular of sample or the tip on the surface. These are called the imaging gas atoms. Okay. And this particular tip is kept at the very sub-zero temperature, at liquid nitrogen temperature, so that you can minimize the atomic vibrations. Then you will apply a very high positive potential, due to which these ions at the surface will go and stick to those terraces, because terraces, as I told you, these terraces have a very high electric field concentration. Okay. And these gas atoms will, the intensity, the very high number of gas atoms will sit at these terraces. Okay. And these terraces get field ionized by the process which I described just before, and it develops the field lines. So you will have a field lines, and these positive gas ions will go and hit to the fluorescent screen by and create an image of the tip surface, of the tip surface. As these gas atoms are atomic at the ionization, so the ionization field is in the atomic scale. Okay. So this field is at the atomic scale, so usually you can see the atomically resolved image of that particular tip surface. Fine. So this is the one field FIM, okay, of of tungsten, which is a BCC, okay, and you can see these concentric rings. These are nothing but the terraces, okay, these are nothing but the terraces along a certain crystallographic direction, okay. Now you can see that these terraces or these rings are having a certain orientation, they have a certain symmetry, and this symmetry is nothing but a stereographic projection of the BCC lattice along 110 direction. Fine. So you are getting a inside the film image you are actually getting the crystallography or the crystallographic orientation of that BCC crystal along 110, and by the symmetry actually you can index these terraces or these rings as different poles or different or crystallographic directions. Fine. So we can index these film images as per the crystallographic directions based on the imaging gas which is hitting on the fluorescent screen. Fine. Okay, so this is just another schematic where little bit more detailed way. So this is just an high mag image of that particular tip which shows the terraces. Okay, so this is nothing but the same principle what I have explained it. Okay, so these are the some examples which I have taken from this particular book, very nice examples. So as I told you, the pure tungsten along the 110 direction you have a symmetry of 110, fine, you have a symmetry of 110, and these are the concentric rings. The second image, it's of a copper iron nickel alloy. This is a particular film image, okay, and in this copper iron nickel alloy it's an FCC matrix where you have a certain precipitate, okay, and you can see that particular precipitate the field ionization has not taken, so means there is no the gas atom, the density of that spots are very less, okay. So in this way you can see that the precipitate in the FIM image, the distribution of in a FIM image, okay. So and here you can see that the nano crystals of pure aluminum, okay, and in an amorphous Al9SM2 alloy. So this is an alloy, and in this amorphous matrix you can see that there is no crystallography associated with this matrix because these spots are randomly arranged, but you can see that there are certain terraces which are like this first location, second location, third location, fourth location, where you can see that these terraces corresponds to aluminum, pure aluminum nanocrystals which are embedded in the amorphous matrix, Some more examples, it is related to the nitrided iron chromium alloy where there are iron chromium nickel nitride platelets, okay. As these platelets has a different composition, the bonding between iron chromium and nitride are different from the alloy iron chromium alloy. So your field evaporation of the gaseous atoms around the tip surface, if these platelets are present on the atom probe tip, then those field evaporation also will be different from the matrix. So these lines corresponds to those platelets which are present in the matrix of iron chromium alloy. Fine. And here there is a very good nice example of a pure iron, and here you can see that these if you remember the previous FIM images, all the concentric circles are exactly at these concentric circles, fine, but here you can see that this particular concentric circle is not finished, it is like this, fine. So this particular the stoppage of this concentric stellar, it corresponds to the dislocation, it's the imaging of dislocation in pure iron, okay. So you can see that how these film images are used to identify the dislocations in the sample or the tip surface. Okay, so with this I will end this class now where we have briefly gone through the physics we have gone to the physics behind the field ionization, and I hope that you have understood the basics related to the ionization of the gas atoms near to the metal surface in presence of the electric field, and how it is different without the electric field. And what is the major takeaway is the electric field should be sufficient enough such that the minimum potential energy should of the gas of the electron inside the gas atom should be equal or more than the Fermi energy level of the metal surface. This will lead to the tunneling of electrons across the tunnel barrier. Otherwise, if the potential energy is not near to the Fermi energy, then the tunneling process cannot takes place. Okay, and second part is the x critical, the critical distance between the electron of the gas atom and the metal surface. So if you go near to the metal surface, the repulsive action takes place, so these tunneling process cannot takes place. So it should be at a certain x critical or more than that, such that the electron tunneling can takes place in presence of the electric field. Fine. And with this I will end this class, and in the next class we will discuss about the electric field, the difference in the electric field around the tip surface and the ideally the sphere, where we explain the point projection model. So whatever the field FIM we are getting it, it has to be reconstructed. So based on the point projection model, we will cover that topic. Thank you.